Mass spectrometry is an extremely powerful tool for identifying the structure of organic compounds. Here are some key points. It will tell you the molecular weight of a compound. For more sophisticated instruments, it will tell you the molecular formula of that compound. It also provides direct information about the weights of fragments of molecules, and that's also extremely useful. It's a very sensitive technique, and that's an understatement. You can use this technique with samples way too small to see. Unimaginably dilute solution can be examined for their composition using mass spectrometry. It does not depend on the use of light, which sets it apart from the other instrumental techniques that we'll talk about. It is destructive. The sample that's actually looked at is consumed. And importantly, for some applications, it's worth noting that the actual examination by the instrument is done one molecule at a time, or more specifically, one ion at a time. Well, how would an instrument like this work? Sounds like magic, and it's close to magic. In a machine, which uses a mass spectrometer, there's an electron beam. These electrons are traveling very, very fast. A sample, which we'll call M for molecule, is introduced into the electron beam. So right here, the electrons collide with molecules of the sample. Now it seems pretty hard to believe, but what happens when you bombard molecules with an electron beam of high energy is you create positive ions. You actually knock out an electron. That's a positive ion, and a dot is placed there because this is not like a carbocation. This is a molecule that's missing a single electron and therefore has a positive charge. A second part of that machine, and those molecules that are now what we call molecular ions, travel through here and they are separated and analyzed. And the analysis tells you the molecular weight, which actually is a reading of the mass to charge ratio. But since the charge is +1, what we're reading is the mass divided by 1, which gives us a molecular weight. If this were all that were happening, it would be very useful. But it's not. In this portion of the spectrometer, the molecular ion is literally vibrating itself to pieces. When that electron smashes into that molecule, it not only knocks out an electron to create a positive charge, but it provides so much kinetic energy that the vibrations that result often cause breakage of bonds. So this molecular ion will, let's say, lose A to form a fragment and perhaps break a different bond to lose something else to make fragment 2. These are positively charged, and a third to make fragment 3. You get the point. A variety of bonds in the molecule may be broken as a result of that excess kinetic energy. And the weights of these fragments are also determined. So now what we know are the weights of smaller pieces of this molecule. And in fact, these may be fragmenting as well to give even smaller fragments. So eventually we're looking at small pieces of a molecule that we can probably identify what it is. At least make a very good guess. If we look at individual fragments, we may be able to figure out how they could have been tied together by bonds to make the actual structure. So, mass spectrometry tells you the molecular weight, it may tell you the actual molecular formula, and it tells you the weights of fragments. In addition, in a mass spectrum, it's important information to see the relative amounts of the fragments that are formed, as well as the relative amount of the molecular ion. So it's going to tell us what are called the relative abundance of the ions that are observed. And the largest one is set to be 100%. All others are given relative abundance in percent relative to the largest one. And this is defined as the base peak. So we have molecular ion, we have fragment, we have relative abundance data, and we have the base peak is the biggest peak observed in the spectrum. Let's take a look at one. This mass spectrum is taken from a database, SDMA. BS. And these organic spectra can be found on the web, and the access is free. I highly recommend using this if you need spectra for organic compounds. This is a mass spectrum for a compound we call 2-butanone. The heaviest peak is at 72, and this is the molecular ion. These are the weights of fragments. So this is 57. This is the base peak. It is 43. Other peaks are much smaller, but notice there's a 29. That's pretty easy to pick out. The vertical axis is relative intensity or relative abundance, with the base peaks being arbitrarily set at 100%, and all other abundances, relative amounts of ion, being set relative to the base peak. And these are the actual mass numbers that correspond to those peaks, which are shown on the horizontal axis. Remember, this is mass to charge formally, but C equals 1, so it's the masses of these fragments. And there is some rationality to how this actually happens. To form the molecular ion, one of those carbonyl electrons is lost, and that leaves a positive charge. The fragments we see to go from the molecular ion to this one is minus CH3, 15. And we can understand how that happens. If this bond is broken to create a fragment where we're losing CH3, the fragment we make permits a filled outer shell of all atoms. So the loss of this methyl group makes a lot of sense. We could say the same thing about the loss of an ethyl group to form an ion that has all atoms with a filled outer shell. And this weight is 43. So breaking the bond adjacent to the carbonyl, losing an ethyl group or a methyl group, makes lots of sense because we form a structure that we've learned is especially stable for an ion because all atoms have a filled outer shell. And that makes an ion by loss of methyl that has a mass of 57, or an ion by loss of ethyl, minus 29. And oh look, we see a little bit of 29, where the positive charge actually remained with the ethyl group. Which brings me to another point, pattern that we see. It will be unique for this exact structure. Like a fingerprint, the pattern of the mass spectrum to positively identify an exact structure if you have a mass spectrum for comparison purposes. Very powerful. Let's quickly take a look at a couple other cases. Here's another molecule. Has the same molecular weight as the 2-butanone we just looked at. So the mass spectrum would give a molecular ion of 72, the same as 2-butanone. But now look, cleavage of this bond, you lose a propyl group, and you have this structure, which has a weight of 29. Cleavage on the other side, you lose a hydrogen atom, and you form a fragment that has a weight of 71. So wouldn't it be easy to distinguish this aldehyde, butanol, from the ketone, 2-butanone, even though they have exactly the same molecular weights, by looking at the fragments that they make? One last example. See how easy it would be to determine whether the carbonyl group of a ketone was at the 4th carbon over or the 3rd carbon over? The fragmentation adjacent to the carbonyl here would lose an ethyl group. On this side would lose a butyl group. The fragmentation adjacent to the carbonyl here would lose a propyl group, and hey, would also lose a propyl group. So the weights of the fragments would be distinctly different. Mass spectrometry, an extremely powerful tool for identifying organic structures.